Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss some problems on module 5. So these problems are available in question bank and this course is Aeronautical Communications. Okay. So already we completed 4 modules, now in 5th module. So what is the 5th module? The 5th module is spread spectrum modulation and air control codes. Okay. So this 5th module having the course outcome is the CO6, that is build the block codes for error detection and error correction in noisy environment. Why? Because the errors are generated in noise environment. So we are going to detect that errors and correct that errors also. Okay, by using block codes. So how to build the block codes are all seen in this module. Okay. Now coming to the first problem. So already we know that the question bank consists of 3 parts in every module. So the first part is problem solving and critical thinking questions, and part B is long answer questions, part C is short answer questions. So here we are going to solve this critical thinking questions. So what is the first one? The parity check matrix of 8,4 block code or C5 is equal to D1 plus D2 plus D4 and C6 D1 D2 D3, C7 D1 D3 D4 and C8 D2 D3 D4. So where D1 D2 D3 D4 are message bits. So what they ask? They ask generator matrix, they ask parity matrix. So in this problem we are going to find the generator matrix. So how to represent generator matrix? G. And how do we represent parity matrix? By H. Okay. By using this information, we are going to generate G and H. So what is the G matrix? The G matrix consists of, in this pattern, what that one? G, IK augment of P. What is P? P is the coefficient matrix. IK is the identity matrix with the size of K. Why? Because here it mentioned 8,4. So 8,4 means N, K. N is the size of the code, block code. So it having 8 bits. The block code consists of 8 bits and the message bits are 4. That is D1, D2, D3, D4. Okay. So we are going to generate G in the form of IKP. So this is a systematic way. Okay. And H, parity check matrix. Parity check matrix. Okay. It is equal to matrix of IN minus K, P transpose, or P transpose IN minus K. So what it may be. So there is a first what you require, coefficient matrix. So how we are going to generate this coefficient matrix. Okay. Now let us start. Yes. So to obtain the generator matrix, we are going to write this C5, C6, C7, C8, which is equal to D1, D2, D3 and D4. So now what is coefficient matrix? So here we are going to simply in this way. Okay. So here this is parity bits. So which is equal to message bits into the coefficient matrix. So again you can write. So what is the size of this one? This is 1/4 and this is also 1/4. And what is the size of this coefficient matrix? The result is 1/4. So it must be 4/4. Okay. Then it is possible for the multiplication, matrix multiplication. So the block codes generation is very easy. We must know the matrices. Okay. Matrix multiplication. Then it is easy to solve. This one. Now it having 4/4. So it starts from P111, P12, P13, P P21, P22, P23, P24, P31, P32, P33 and P34. And the last one is P41, P42, P43, P44. So this is my 4 by 4 coefficient matrix. Now I am going to multiply this row into the column. So we are having only first one row, single row. So the single row is multiplied with the 4 columns. Okay. So hence C5. This is my C5. The first one is C5. So that is D1 into P11, or you can write the coefficient matrix first, no problem. That is P11 D1 XOR P21 D2 XOR P32 D3 XOR P41, sorry, this is not 32, P31 and P4, this one. This is my first row multiplication. When you multiply the first row with the first column, you get the C5. Okay. So once again you see D11 P1, D2 P21, D3 P31, D4 P41. But here we are using the XOR operation, Master Shoot. So you know the XOR operation. For example, 1 XOR 0. What you got? 1. 0 XOR 0. What you got? 0. Okay. And again 1 XOR 1. What you got? 0. 0 XOR 1. You got 1. In this way, we are going to generate. So already you know this one. Okay. And next one is C6. So C6 is P12 D1, P22 D2, P32 D3, P42 D4. And again C7, P13 D1, P23 D2, P33 D3 XOR P43 D4. And the last one is P14 D1 XOR P24 D2 XOR P34 D3 XOR P44 D4. Okay. So this is my multiplication of message matrix with the coefficient matrix. Okay. Now we are going to compare with the given check bit equations. So what are the given check bit equations? You go for the question. So what is given? C5 equal to D1, D2, D4 present. D3 is absent. Okay. And again C6 equal to D1, D2, D3 present. D4 is absent. So in before we are going to multiply this message matrix with the coefficient matrix, coefficient elements. Then we are going to substitute this message values where it present. Okay. Then you get what is C5 and what is C6, what is C7 in terms of coefficient matrix elements. Okay. Yes. So comparing the above equations with the check equations, check bit equations. So P11 is equal to 1. P21 is also 1. P31 is 0. P41 is 1. Okay, why? Because here you go to D3 is absent. In C5, D3 is absent. So here in C5, this D3 is 0. not having. Okay, why? Because D3 is 0. 0 into anyone gives 0. Okay, so what they left? D1, D2, D4 present. So P1, P2 1, P4 1 are 1s. Okay, similarly, this P12 is 1, P22 1, P32 1, P42 is 0. So again, P13 1, P23 0, P33 is 1, and P43 is 1. P14 is 0, P24 is 1, P34 is 1, P44 is 1. Okay. So we are find the elements of the quotient matrix. Now we are going to substitute this quotient elements in the quotient matrix. Now the P matrix, hence P matrix is equal to 1, 1, 1, 0 first. Next P2 1, 1, 1, 0, 1. Next third one 0, 1, 1, 1. Next last one 1, 0, 1, 1. So this is my 4 by 4 quotient matrix. Okay. So what they ask? They ask generator matrix. So it is the form of IK P. IK is the identity matrix, P is the quotient matrix. Okay. So coming to substitute, this G is equal to identity matrix size is 4 by 4. So 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 3 zeros 1. Augment of P. So what you got P? 1, 1, 0, double 1, 0, 1, 0, triple 1, and 1, 0, double 1. So this is my 4 by 8 generator matrix. 4 by 8 generator matrix. Okay. Now, by using this generator matrix, you can generate the code. For any code generation, G is must generator. So, for generation of G, coefficient matrix is must. So, in this way, you are going to find the coefficient matrix. Okay. And next one is P transpose I n minus k. This one. P transpose. Where in G, P is normal form. But coming to the parity check matrix, this coefficient matrix is goes to transpose. So the rows becomes to column, column becomes to row. Okay. So here we go to substitute this one also. So what is my P? 3, 1, 0 in the first row. Again this comes to column. So 3, 0. And here double 1, 0, 1. And here 0, triple 1. And 1, 0, double 1. This is my P transpose. And I n minus k. What is my n? 8. K is 4. So 8 minus 4. Again it is also 4 by 4. So 1, 0, 0, 0, 1, 0. This one is my parity check matrix. Okay. So in this way, we are going to find the generator matrix and parity check matrix. Okay. So all these problems are in this way, in this question bank of module 5. Okay. So this one, second one, the generator matrix of 6,3 block code is given below. So this is my G. Find all the code vectors of the code. So here 6,3 means n, k. So my n size is 6, my k size is 3. So my n minus k is 3 also. So how many code vectors are get from this general matrix? So simple, 2 power k, that is 2 power 3. So it is 8. So 8 message vectors are come, or 8 code vectors. So from this 8 message vectors, we are going to find 8 code vectors. Then another doubt, how to get this message vectors? So it is a 3 bit. It mentions 3 bit. So that means 0, 0, 0 starts. Okay. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, double 1, 0. This one. That means from 0 to 7. When you convert this decimal, 2, 3, 4, 5, 6, 7. Okay. So for 0, you have 3 zeros. For 7, you have 3 ones. So how many messages are there here? Count 8 messages. So this is 8 messages. For this 8 message vectors, you get the 8 code vectors. Okay. So it is also simple one. Okay. So coming to this problem. So Z. What is my Z? Here I am going to write 1 0 0 0 1 0 double 0 1 and augment of P 0 double 1 1 0 1 double 1 0. So this is my Z. Okay. So N is 6, K equal to 3. So N minus K is 3. Why N minus K is a parity bits. So N minus K parity bits are going to add. So what is in the form of G? Ik augment of P. So the left hand side is the identity matrix and right hand side is the coefficient matrix. Okay. So from this I can write my coefficient matrix 0 1 1 1 0 1 double 1 0. Okay. So after getting the coefficient matrix, I am going to get the parity bits, parity check bits or check bits, simply what it may call. So for this C equal to M into P. C is the parity check bits, C check bits, M is the message, P is the this coefficient matrix. Okay. So how many parity bits? N minus K. So parity bit size also 3. So that's why C1, C2, C3. If N minus K is 4, then I can use C4 also. Okay. So C1, C2, C3 matrix is 1 by 3. The matrix size is 1 by 3 and this means single row, 3 column. And my message is also M1, M2, M3. 3 messages is multiplied with this 0, 1, 1, 1, 0, 1, double 1, 0. So this NF. This one. Okay. So what is this one? This size 3 by 3 and this is 1 by 3. So the result one is 1 by 3. Okay. So here you can write my C1 is equal to what you got to multiply this first row with the first column. So M1 is 0, M2, M3 is present. So M2 XOR M3 is first parity. Next, M1 is multiplied with the second column. So this is first one, this is second one. So M1 C2 is equal to M1 XOR M2 is absent 0. So M3. And again C3 is equal to M1 M2 present where 0 is absent. So M1 XOR M2. Okay. So we are having 3 parity bits. Okay. So whatever may be the message bits, it is going to XOR operation and generate the parity, 3 parity bits in this way. So in this problem they ask to find all the code vectors. So here I am taking the serial number in 1 and a message vector M. It consists of M1, M2, M3 and a check bits C, C1, C2, C3 and finally code vector X. Okay, so finally what you go to generate. Okay, so first 0 0 0 2 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 0 8. So 8 message vectors. For this 8 message vectors, 8 check bits are generated. So for C1, what do you use? M2, M3. For C1, M2, M3 XOR. So M2, M3 XOR. You are going to M2 value is 0, M3 value also 0. So 0 XOR 0, simply 0. What is C2? M1, M3. So M1 also 0, M3 also 0. So it is also 0. C3, M1, M2. So this also 0. So what is my code? Here the first is message and next my parity check bits. So these 3 and these 3, 6 bits are generated. Okay. Next is 0 0 1. For again C1, it is M2 XOR of M3. So it is 1. And C2, what is C2? M1, M3. M1, M3. So this is also 1. And last one C3 is M1, M2. So M1, M2 are zeros. So 0 XOR 0, 0. So what we generated? The code M1, M2, M3. So C1 is 1100. Okay. So in this way you can generate all the 8 code vectors. Just what is C1? M2 XOR M3. What is C2? M1 XOR M3. What is C3? M1 XOR M2. So I given all the 8 bits, 8 message vectors, and these 8 message vectors going to generate 8 check bits, and you are getting the combination of this message and check bits to get the code vector. Okay, so for this 101, for this 011, and again this also 011, 101, 110. Last one is again all zeros. So you get right 010, 101, 011, again 011, 100, 011, 101, 101, 110, 110, 3 ones, 3 zeros. Okay. So this is my all the code vectors. Okay. Coming to the another problem. So this is my third one. Consider 7,4 black code whose general matrix is given. So this is my Z. Consider 7,4 Hamming code. So simply they ask code matrix or code or simply black code. So from this here you can see for any problem you must find the n value. So n value is 7, k value is 4. N minus k is 3 parity bits, 3 check bits. 3 check bits, 4 message bits. Finally, 7 code. My code size is 7. Okay. So here they didn't give any message, so we can take any of this message. So how can we get message? Its message size is 4. So 2 power 4 is 16 message vectors are there, and message size is 4 bits, like 4 zeros to start, 001 up to 4 ones. So this is the 4 message vectors. For this 16 message vectors, I can generate 16 code vectors. Okay. Okay. What is my G size? IK in the form of IKP, and my G size is 4 by 7. You can see 4 rows, 7 columns. So here 4 by 7. This is my G size. My generator matrix size is 4 by 7. In this generator matrix, it is in the form of IKP. IK is the identity matrix of size K. K is the message size, and P is the quotient matrix. So from this you can find the 16 code vectors. Okay. So how can you generate a simply in this way? Also you can find this code. Okay. So for example, my M is 310. Y K is 4. Okay. We know the G. Okay. Then I am going to find the code in a simple way. You can see X into MZ. 110. What is this size? 1 by 4. So what is my G size? My generator matrix size is 4 by 7. So this is my 4 by 7. Then I can get 1 by 7 size. Okay. So first is identity matrix. This is first row. 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 101, 0, 0, 1, 0, 1, 1. Okay. So here it is in the form of IKP. So this is IKP. Identity matrix and coefficient matrix. Now I am going to multiply. Here multiplication means I am operating the XOR operation. Okay. So let us see. First row, first element 1. Here the first column. So this is my first column. So 1 into 1. 1 into 1. Here I am showing 1 into 1. XOR 1 into 0. XOR 1 into 0. XOR 0 into 0. Here 0 into 0. 0. 1 into 0. 0. And 1 into 0. 0. 1 into 1. So this will remain. So what you get? 1 XOR 0. 1. 1 XOR 0. 1. 1 XOR 0. 1. So my first element is 1. Okay. Similarly, 1 into 0. 0 XOR 1 into 1. S1. So 0 XOR 1. I got 1. Remaining all goes to 0. Similarly, third element also 1. Fourth element is 0. Now the parity bits. So here 1 into 1, 1. XOR again 1 into 1, 1. So 1 into 1, 0. 0 XOR 1. I got 1. Okay, so remaining 1 into 1, 1. XR 1 into 1. So 1 XR 1, 0. So 0, remaining all also 0. And the last one, 1 into 1, XR 0. So 1. Again 1 into 1 XR 1, 0. So the last one also 0. So this one. So this is my code. What is my code size? 1 by 7. So in this, we can observe what is a message. 1110. Why I am given this one? 1110. This 1110 also appears here. So this is a systematic way. Why? Where G is in the form of IKP is called the systematic pattern. So in the systematic pattern, we can easily identify where the message bits are located. Okay. So in this way, you can generate all the 16 code vectors. Okay. And now, fourth one. In a 6,3 block code, the parity check matrix is, so here H is given. Okay. Here H is given and determine generator matrix, all possible codes, error detection and correction capability. Error detection, correction. Okay. Okay, very good. So here I am using my H is 110 100 0 11 010 101 001. So this is given H. So this is also N comma K pattern. So N is 6, K is 3. So N minus K is 3. So 3 message bits and 3 check bits. Okay. So what is H pattern? P transpose augment of I N minus K. Okay, I N minus K pattern. So my N minus K is also 3. My message is also 3. Okay. Now P transpose is equal to, so this is my P transpose 110 0 11 101. So here we are going to this P transpose again. Then what do you get? P. Okay. Here P transpose is there. So I am going to transpose again. What do you get? P. Normal P you got. So for this I am going to convert rows into column into rows. What is the first row? 110. So now it is written as first column. Second row 011. Again it's coming into second column. Third row 101. Now this is third column. Now this is P. So what they ask? Generator matrix. So G equal to IK augment of P. IK augment of P. Okay. So IK is identity matrix of with K size. So 1 0 0 0 1 0 001. This is my identity matrix. And my P 101 110 0 11. So this is my generator matrix of size 3 by 6. 3 by 6. Okay. So what they ask? All possible codes. So X equal to M into Z. Already I shown how to generate directly. Okay. Directly we can generate. Just to go to multiply message you get. Okay. So in this way you go to find all the messages. And another one, they ask how many errors can be detected and how many errors can be corrected. Okay. After generation of all code vectors, you can find this error detection and error correction after transmission also. Okay. So this is in transmitter size. In transmitter side, I am going to generate these codes. So I am going to transmit these codes and the receiver receives. So why? The receiver receives the signal in a noise environment. So errors may generate. So how many errors are there in my code and how many errors I can correct? Here I am using the linear block codes. Okay. So D minimum is greater than equal to S plus 1. So this is the formula. So what is D minimum? Minimum distance. So minimum distance we can take. Or how many ones are there? That is weight. Okay. Minimum weight. So for the black code, minimum weight is 3. So how can you know this one? After you are getting a code from x equal to m into z, then you can, for simple, you can take any one, you get to multiply that. For example, my x is for example this one. For example, so here what is the minimum weight? Minimum weight means minimum number of ones. How many ones are there? So this is can be also called weight of the code. So here this is 3 greater than equal to s plus 1. Okay. So what is my s? Is less than equal to 2. So it means I can detect less than equal to 2. So maximum I can detect 2 errors only. Okay. How many errors I can detect? I can detect only 2 errors. And how many errors can I correct? By using these black codes. Okay. So that is day minimum greater than equal to 2t plus 1. 2t plus 1. So here how many errors can be corrected? Okay. So here also I take the minimum d minimum distance is 3 greater than equal to 2t plus 1. So again we can shift this 1 to the other side. It is 2. So my t is less than equal to 1. So I can correct only one error. I can detect 2 errors, but I can correct only one error only. Okay. So this is my solution for this for that fourth problem. Okay. So this is fifth one. Here again H is given. The parity check matrix 7, 4 linear block code is given below H, and H matrix is given. And here calculate the syndrome vector for single bit error pattern. So here S equal to R into H power T. Simply you can find the syndrome. So what is our received vector? So I get any received signal. From that received signal, I can generate the syndrome vector. Okay. For example, my received is this one. Okay. This is my received. So this is my H. H transpose. So H transpose is, so row as column. So 1 1 0 1 0 0 0 1 1 1 0 1 0 double 1 0 1 double 0 1. This is my H. Then I go to multiply this R into H power transpose. Then I get syndrome. So what is the size of this R? 1 by 7. This size is 7 by 3. So what do you get? My syndrome size is 1 by 3. only 1 by 3. So those 3 are the check bits. So here you can find where that error is located. For example, after multiplication of this one, I get 3 zeros. So there is no error. That means the correct code will receive. Okay, at the receiver. For example, it may be the middle bit is 1. What this 1 indicates? The middle bit is error. One error is there. Or whether it is located at first position, then it is also indicates the first position of the syndrome is error. So in the previous problem, we have seen how many errors can be detected. So that is based on the minimum weight of this code. Okay, so we can identify 2 errors. We can detect 2 errors. We can correct only 1 bit error. Okay, so in this way you can identify all these syndrome patterns. Okay, so this is also G. So the 6th problem, a generator matrix of 6,3 linear block code is given as Z is equal to 1 0 0 1 1 and 0 1 0 1 1 0 0 0 1 0 1 1. So this is my Z. So it is in the form of IKP pattern, argument of IKP pattern. If the received signals is determine the message bit sequence. Okay, so it is similar to the previous problem. What that one? Here you go to calculate the syndrome. After syndrome, there is any error is there, you can correct that error. Only 1 bit. Okay, so determine the message sequence and D minimum. Okay, so first you convert this G into H. So what is H pattern? P transpose augment of I n minus k. P transpose of I n minus k. So this is my P. So P transpose. So first rows converted into columns. So 3 ones come to 3 columns. 1 1 0 0 1 1. And augment of I n minus k. So I n minus k means 6 minus 3. Again 3 by 3. So 1 0 0 0 1 0 0 0 1. So here it is a 3 by 6 size. 3 by 6 size. So here the received is also 1 by 6. Okay. So O into H power T. Okay. So syndrome is equal to R into H power T by R. The received one is 101, again 101. So 101, again 101, this one. So this is my received size 1 by 6. So here my H is 110. This is H, but I require H transpose. So again the rows is converted into column and column converted into rows. Okay. So 110. So H transpose is 110 1 0 0 111 0 1 0 101 0 1. So this is my H transpose. Okay. So now I am going to substitute. So first one is 3 ones. So first 3 ones. 110 0 110 0 0 1 1. 0 double 1 1 double 0 1 double 0 0 1 0 0 1 0 double 0 1 double 0 1. Okay, so this is my h power t. So now I am going to multiply this one. So this is 6 by 3. Okay, so 1 into 1 1 XR 1 into 0 0 into 1 0 XR 1 into 0 0 XR fourth bit is 1 1 into 1 1 XR and another one is 0 into 0 0 XR 1 into 0 0. This is the first one. Again the second column equal to multiply 1 into 1 1 XR 0 into 1 0 XR 1 into 1 1 XR 1 into 0 0 XR fifth one 0 into 1 0 XR 1 into 0 0 XR third one 1 into 1 1 XR 0 into 0 0 XR 1 into 1 1 fourth one 1 into 0 0 fifth one 0 into 0 0 XR 1 into 1 1. So this is my syndrome. So here 1 XR 0 1 again 1 XR 0 1 1 XR 1 what you got 0. So first one is 0. Second also 1 XR 0 what you got 1 XR 0 1. So 1 XR 1 again 0. So 0 XR 0 0 0 that is 0. Next 1 XR 0 1 again 1 XR 1 0 0 0 0 last two again we have 1. So 0 XR 1 1. So it indicates error is there. So third bit is error. Third bit is error. Now here I am going to identify where this error in the bits. Okay. So go for Z. So Z is IKP. So IKP indicates systematic. So systematic means this 101 101 is there. So this is message bits. So the errors are generated in parity bits only. Okay. So here we got third bit. So here this third bit this one. So this is error. So simply we can convert this as 0. So this is my message sequence. So what is the minimum? Day minimum. Here 3. This one. Okay. So we have a doubt whether it is correct or wrong. What to do? Again we are going to multiply this R into H power T. Then you get 3 zeros. So you can conclude there is no error. Okay. So in this way you can find any message sequence. Okay. So seventh one is prove that C into H power T. Here C H power T is equal to 0. What that one? What is C here? C is code word and H is the parity check matrix. So when you go to multiply code into the transpose of parity check matrix, it results 0. You go to prove that one. Okay. So here in simple way I am going to conclude this one. So what is my code here M into Z I can generate. Already we seen in the previous problems. Okay, M is message, G is generator. Okay, so and again G is in the form of ik augment of P. This is my G. What is H? H equal to P transpose I n minus K. So this is the general systematic pattern of G and H. Okay. So here C into H power T. C H transpose is equal to 0. So what C contains? M into Z. Okay. So here first G H power T we are doing, that is equal to IKP P transpose I n minus K. Okay, and again this one P transpose. This is G H transpose. Okay, so again IK P and P transpose of transpose. So it returns P, and this is I n minus K. So already we know that P XOR of P or modulated sum of P. For example, 1 XOR 1, what will result? P. So here also this G H power T goes to 0. Okay. Then C into H power T is equal to M into G into H power T. So here G into H power T. So this one is 0. So M into 0 gives 0. So simply we prove this one. Okay. Next one is 8th bit. The generator polynomial of 7, 4 cyclic code is G of P is equal to PQ plus P plus 1. Determine the code vectors in a non-systematic form for bits 0, 1, 0, 1, 4 ones and 3 zeros 1. Okay, simply you can do. We are considering the first one. So this is data bits or message. So M of P. So here this is in code form. We convert this into polynomial form. Why cyclic codes are in polynomial forms? Okay. So here 1 P square PQ is there. Okay. But what the present? P plus PQP is present. So this is my message polynomial. And what is my generator polynomial? PQ plus P plus 1. Or we can return 1 plus P plus PQ. So generally increasing powers. Okay. So 1 plus P plus PQ. M of P is P plus PQ. What they ask? Code polynomial C of P in non-systematic, not in systematic. Already we've seen in some solved problems on cyclic codes. I already explained what is systematic and what is non-systematic. Okay, in non-systematic, you just multiply the message polynomials into generator polynomial. Easily generate. Okay, that is M of P into G of P. So for example, here P plus PQ 1 plus P plus PQ. Okay, so first one is P square plus P to the power of 4 plus P cube plus P4 plus P6. Okay, so here P4 terms are there too. So simply XOR operation. Not P4 plus P4 is 2P4. So here in block codes or cyclic codes, 1 XOR 1, what returns? 0. So the P4 term is absent. So what you get? P plus P square plus PQ plus P to the power of 6. What they ask? Generate the code vector or code polynomial. What is the size? 7, 4. So you have a doubt. Then we convert this one again into bit form. Okay. So here 1 is absent. So 0, 1, 1, 1, 4 absent, 5 absent, 6. So this is my code vector, code block. So totally 7. So my code size is 7. I generated the code size. So in this way you can multiply the remaining 2 also. Then you get this non-systematic form of code polynomials. For systematic, there is a pattern is there. Okay, that already shown in previous videos. You can follow that one. So ninth one. So in a 7, 4 Hamming code, the generated matrix is Z, parity check matrix, all possible codes, error detection, error correction capability. So this is also previous 7th one, I think, 6th one, 6th problem. So G is in the form of IK argument of P form. Okay. So from this, you go to generate the H, that is P transpose of I n minus K. Then parity check matrix is generated, all possible codes. So here also you get 16 code vectors from 16 message vectors. Why? Because 2 power k, 2 power 4 is 16. So 16 message vectors going to generate 16 code vectors or 16 codes. So all possible code means 16 codes you go to generate. Already shown error detection and error correction capabilities. D minimum. Minimum distance is required. After generation of any code, you get the minimum distance. How many non-zero elements. So that is the weight of that code. Okay. So from that, you can use that. Okay. So coming to the last one. So calculate the minimum distance weight of the code, Hamming distance for the given U 1010, V is 0, 111, W equal to 1001. So Hamming distance is the number of positions in which the string differs. Okay. So that is the Hamming distance. So get U XOR V XOR W. So for example, what is my U? 1010 XOR of V 0 1 1. Okay. So 101. What you got? 101 011 0 1. This is my result. This XOR with W 1 0 1. So 1 XOR 1 0 1 0 0. Okay. So this is 0 1 0. So that is when you XOR of these three. But here weight of the code. So the weight of the code of this one is finally 1. Only one non-zero element. Okay. And here Hamming is number of positions vary. So when you compare with the U to 1, here it is varied. But there is no variation. Okay. So here 3 variations coming from U to V. Again from V to W. Also 3 variations. Okay, so that is the ammunitions is 3. You can easily find. Okay, this is the minimum weight. Okay, I think you understand. Thank you. So for development of this content, I use Saman Hacking, Sanjay Sharma, and Jess Chitori also. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.